Hi, I'm recording a hopefully short video to catch us up on the lecture material. We didn't quite get through everything today in class for lecture 15, so I thought I would try to cover the last little bit in this video. We were talking about Valgrind at the end of the lecture, and I just talked about the experimental SG check option. We talked about how that may be able to find some errors with stack or global variables. You can run either this or the regular memcheck tool. You can't turn them both on at the same time. But if you're trying to catch both types of errors, it would make sense to run with one of the tools and then with the other one to see if either of those can catch problems. We talked about the output you might get from SGCheck, and we saw that in this case, it found two other errors with our program that were missed by the regular memcheck tool. I've taken a little bit of time to try to help you make sense of the Valgrind output. I think that's one of the things that you'll want to be able to do because it'll probably be the easiest tool to use for finding errors, especially with heap allocated memory. So I thought we'd take a look at some of these errors and just try to connect them up, connect up the report you might get from Valgrind with the code that might produce that error. So here I'm dynamically allocating an array of 10 integers called list. So as an array, if it's got 10 integers, 10 slots, then they're indexed 0 through 9. So what I'm doing here is an error. I'm right past the end of it. I'm trying to get an item out of the array or get a copy of an item. So that would be a read for the array. If I ran this in Valgrind, I would get an error message like this, and you can see it says invalid read of size 4. Size 4 because it's an array of ints, so each of those integers is 4 bytes. So it's seeing that I'm trying to access 4 bytes of memory right past the end of the array. We talked about this earlier in lecture today. The starting address that I'm trying to access is right past the end of the array. So that's 0 bytes after this block. It's right past the end of the block. You can compare that to the next error here. I'm backing up one element before the start of the array. It's kind of obvious because I'm using an index of -1. The compiler will let you try to do that, but for this array, that's also an out of bounds access. Here I'm trying to store something in the array, so that gets reported as an invalid write, still size 4, because it's an integer. But here you can see the effect of that starting address of that 4-byte spot right before the start of the array, whereas here I'm right past the end, so it says 0 bytes after. Here I'm trying to access it's a 4-byte slot in each element of the array. So if I'm accessing before the start of the array, that would be the start of that element at index -1 would be 4 bytes before the start of the array. So that's what it reports down here. So these are the kinds of errors that you'd get if you were off the end of an array. If you were further off the end, rather than just one element away, that would show up in these number of bytes after or number of bytes before reported. One error that's really common for students to run into is when Valgrind catches you using uninitialized memory. That's what I'm showing off here. Usually the way it'll report that is when you have some kind of a test based on uninitialized memory. And that's what I'm doing in this code. I allocate some heap memory, and then I look at what's on heap memory and use that to make a decision in my code. But since heap memory is uninitialized, Valgrind complains because, well, who knows how this test is going to go if you never put anything in the memory you just allocated. Here, I'm kind of doing it directly. Here, I'm trying to make it a little less obvious by copying an element out of this dynamically allocated array and then looking at that. But in either of these cases, Valgrind catches that, and it reports this as conditional jump remove depends on uninitialized value. Here, it's kind of obvious why I'm getting that, because I'm using uninitialized heap memory. Another place that it's common to run into this is if you forget to put a null terminator at the end of the string. The standard library functions will generally null terminate your strings for you, but if you build a string by copying a character at a time into an array and you never put the null terminator, then any code that tries to print that string, or even if you call string length, it'll give you a report like this in Valgrind, because when it gets to the right past the last character you put in the string, usually the place where the null terminator should be, once you get there, you're accessing uninitialized memory if you never put a null terminator there. So you'll get a report like this, maybe from code that you wrote, or like I said, maybe you pass that string to a function and you get this kind of complaint from that function. Valgrind can report memory leaks. We said at the end of execution, it will report any leaked memory. And that's what I'm doing here. I allocate some heap memory, but I never free it. And it complains at program termination that this block of 100 bytes that you mallocked was never freed. And you can see 100 bytes in one block was lost when your program exited. You can do something similar to look for file leaks. There's a different option for this, but if you wanted to report on leaked files, there's a --track-fds equals yes option, and this makes it report on any open files you have at the end of execution. Now here I open one file that I never closed, but when it reports on my files, it says I have 4 of them open, but that's because it's counting the 3 that you get for free: standard input, standard output, and standard error. So even a correct program would have 3 open files at termination. You're normally not expected to close those. But if you have more than 3, then that would mean you opened a file and you forgot to close it. Here it tells you, kind of like with leaked memory, it tells you where you opened that file that you never closed. And that would give you a chance to think about where maybe you should have closed that file. I mentioned that Valgrind is a dynamic analysis tool. It watches your program as it executes and tries to catch it doing something wrong with memory. There are also a variety of what are called static analysis tools that try to find bugs in your program just by, well, kind of like an expert might do, by looking at your code and trying to see if you've done anything wrong in the code. Now, a program might not be able to do that like a human expert, but human experts have built programs that look for common mistakes in code or places where you might have created something like an array and then accessed past the end of that array. And they've got built-in rules for looking at these kinds of things. There is a tool for static analysis that should be installed on the common platform machines that you can try out. We'll be trying out a CPP check. You can see from its name, it's kind of made for C++, but since C++ is generally a superset of C, it can also be used to detect errors looking at C code. So this is that same piece of code that we looked at before with Valgrind. It makes 3 arrays, one on the stack, one on the heap, and one statically allocated. Each of them are 10 elements, but I got a piece of code down here that goes 1 element past the end. This mistake, especially highlighted in red, it's kind of easy to catch, and it's easy for the CPP check to catch an error like this. This is the kind of thing that it has rules built in to help catch. The way you run it is you run CPP check, and then you give it your source code as an argument, and it'll look at that source code and apply all of the rules it knows for detecting common errors, and it'll report what it finds. You can see in this case, it found all 3 of our errors. It found for the statically allocated array that we indexed at index 10, which is out of bounds. Same thing for the stack allocated array, same thing for the heap allocated array. CPP check can do a pretty good job catching some of these errors, but no program could really catch every error like this. And in this case, I kind of made it easy for CPP check. Backing up a slide, here's where I allocated the arrays, and right down below this is where I use them. So it's pretty easy to see that if they're all 10 elements, I'm going 1 past the end of each of these arrays. If I make this a little harder for CPP check, I can, well, here, instead of putting the code that accessed the arrays right here in main, I put it in a function. It's still the same code. It accesses the array as if there are 11 elements. but I make three 10-element arrays, and then I pass each, or I pass, yeah, each of those arrays to this function. And so instead of having the code right here that's got the error, it's kind of hidden up in this function. And unfortunately, that's enough to fool CPP check. If I run that on this slightly modified program, it will miss this error. It doesn't report any errors with this slightly modified program. I guess this is a reason it's good to have a variety of tools. We mostly looked at dynamic analysis tools, but it's good to have access to several dynamic analysis tools and some static analysis tools. If any of these catch an error, that's something that's worth following up on. We have one more topic. We skipped over this during regular lecture, so we could go ahead and look at Valgrind. But another instrumentation option offered by GCC is it will build in support for measuring code coverage as your program executes. And this is usually to support your test plan for your code. Code coverage lets you measure or lets you keep up with which lines of your program actually got executed. And then if you're testing the program, you can get an idea of which parts of the program had a chance to execute under test and which ones didn't. That might let you design some additional test cases or unit tests to try to make sure you've exercised more of your program to give you more confidence that that program is actually correct. We're going to take a quick look at the GCC options for adding in measuring of code coverage. And this will let us, during a program, it'll let us look at which statements got executed and which ones didn't. We can even look at the program in finer granularity and see what happens, which paths through the execution got executed and which parts of a conditional got a chance to do their thing. I checked with one of your CSC 216 instructors, and I know you've gotten a chance to do this kind of thing in Java. We'll just be looking at some tools to do some of the same things in C. To compile a program with support for code coverage, we're going to use two new options. You can see they both start with this -F, and that was the same as we had for our other instrumentation options. We're asking the compiler to put in extra code, in this case, to measure which parts of the program have been executed and which ones haven't been executed. So the options we need are -F, profile, -args. And I've split this across two lines here, but you'd normally put this all on one GCC line. So -F profile -args and -F test -coverage. All right, I brought a program we can try out for code coverage. It's a simple bubble sort implementation. Let's take a quick look at the source code, and then we'll try building it with support for code coverage, and then try testing it some and see what lines of code get executed under test. So for this program, it does bubble sort on an array of up to 25,000 integers. Down here in main, I make the array. I got a function called readList that reads a bunch of values from standard input and stores them in the array. It puts all the values in this, whatever you pass in as the list parameter. So that's this array with room for 25,000 values, and it returns the number of items it successfully read. I've got a sort list function where you give it the array and the number of items in the array, and it does a bubble sort on that. And then I've got a print list. Let's look through each of these functions real fast. Read list, well, it expects the first input to tell you how many values are going to be on the list. So I try to read that, and if I can't successfully read it, I've got a function, it's defined right up here, that prints out an error message that you provide and then exits unsuccessfully. So if I can't read the number of items, I complain and exit. And then if I can read it, I go through and try to read that many items from standard input, storing them in the next spot of the list. And I do the same thing here. If I ever fail to read one of those, I print out an error message and exit. After I've read in the list, I call sort list on it. This is a typical bubble sort. You remember bubble sort. It takes an array of items, and it goes through the array from front to back, and it looks at adjacent items in the array. And if it catches two items out of order, it swaps them to put them back in order. And that's what this inner loop is doing. So I'm going to go through everything in the array. And if I catch two items that are out of order, I've got a swap function that rearranges them. You just have to give pointers to each of the items. You can see I'm using pointer arithmetic to do this. If list is my array, then list plus j would be a pointer to the jth item. And list plus j plus 1 would be a pointer to the next item in the array. So I give swap pointers to those two elements. Swap, it's defined up here. It expects two pointers to integers. And then with the help of a temporary variable, it swaps what's in those two integers. So I go through the array and I swap any pair of items that are out of order that I catch. The problem is with bubble sort, just going through the array once like that, start to finish, that doesn't guarantee that the list will be sorted. You have to make multiple passes through the array. So that's what this outer loop is doing. I keep going through the array, doing this inner loop over and over until I get the list in sorted order. And one way to check for that is if you ever make a pass through the whole array and you never see any two items that are out of order, then you know the list is in sorted order. So that's what this done flag does. Whenever I swap two items, I set the done flag to false. If I ever get through the whole array and the done flag is still true, then I'm done, so I can exit. So this outer loop stops whenever done is true. And even if you never made a pass through the array and found that all items were in order, you still only have to make so many passes through the array until you're guaranteed that it's in sorted order. So that's what the second part of the condition does. Once you've made enough passes through the array, you know you can stop, even if the done flag didn't let you stop earlier. And then, so after, if you got an array of n items, then you don't have to make more than about 10 passes through the array to get it into sorted order. Once the array's in sorted order, I call this print list function. It just goes through and prints out each item, all on a single line with a new line at the end. So this is my bubble sort implementation. I've got a test input that we can test it on, and then we can see what parts of the code were executed under test. So I've got, these are our example programs for today. So I've got a bunch of examples that we've already looked at, but here's my bubble sort. Let's compile it with these two new options we just talked about for measuring code coverage. So GCC-wall -std equals C99 -g and then -f test coverage -f profile arcs, and then my source file bubble.c-o bubble. That looks good. Yeah, so it compiled, and if you look, you can see here's our executable bubble, and my terminal colors it green because it's marked as executable. But you can see the compiler also gave us this extra output file. This .gcno is part of the code coverage support. You can think of it as a file that maps from executable instructions in the program back to lines of code in the source file. So as the program is executing, that lets it know, well, what line of code was I executing there? So you can tell which lines got executed and which lines didn't. Now, the way this code coverage support works is it builds your program with support for measuring code coverage. Once you've done that, you can just run the program normally, and every time you run it, it will keep up with which lines got executed that last time you ran it. So if we want to run it, bubble, and I've already got an input file. It's called small input here, I think. So let's read from that file, small input. And this program will read in, it'll expect first, how many numbers do I need to sort, and then a list of numbers. And then it prints them all out, and you can see, well, I don't know what the input was, but that looks like a sorted list. So it looks like it at least did the right thing. But I wonder how much of the program got executed, or which lines got executed under test, if we think of this as sort of a simple test case. If we take another look at our files, you can see, well, that last time I ran it, a new file got created, this .gcda file. You can think of that as a GNU code coverage data file that keeps up with which lines got executed when I ran the program. And every time you run the program, this file gets updated to record, well, what new lines got executed the last time you ran it. So the idea is you could, instead of just running it once, you could run it with a bunch of tests, and every test might contribute some lines to this data file. Now, if you look at this data file, you'll see that it's not a text file. You can't make sense of it very easily in an editor, but there's a program that will tell you, that can interpret this file and will give you your code coverage information in a format that's easier to read. And that's GCOV, G-C-O-V. Will give you a code coverage report based on since you last recompiled this program, what stuff got executed. You just have to give it the name of the source file that you want coverage information for. So for us, that's bubble.c. And it gave me a quick summary here on the command line. It says I was looking at bubble.c and it had 36 lines of code. Now, the file was longer than that, but a lot of those were comments or blank lines, or maybe like a closing curly bracket, something that doesn't really execute on its own. If you just look at the parts, at the statements that are executable, there are only 36 statements in there. And I didn't get them all executed under test. Only about looks like 2/3 of them got executed. If I was wanting to try to do a good job testing this, I'd probably want to add some more test cases to try to get those code coverage numbers up. But to know what test cases to add, it'd be nice to know which lines got executed under test and which ones didn't. And that got written out in this bubble.c.gcov. Let's take a look at that. Bubble.c.gcov. And this file shows, well, it's got some information at the top, but most of this is my source code. Same as what we looked at before. This part over here shows what lines got executed under test. And this 5 pound signs in a row is actually a line that could have been executed, but didn't get executed. So you can see, kind of oddly, this swap function never even got called. Well, maybe no surprise, this error handling function didn't get called during my most recent execution. Readlist got called, but the little lines where it called the error handling didn't get executed. Here in my bubble sort function, this little bit of code never got executed. And here I'm showing you those places where there are 5 pound signs in a row. Again, that's a statement that could have been executed, but it hasn't been executed yet since you recompiled it. So when you're looking to add more tests, those are the lines that you want to concentrate on. Lines that just have a number, that's showing how many times that was executed. So this if statement got executed 4 times. This setting done to true got executed 1 time. So those are ones that are already getting executed at least some. Ones with a dash are lines that didn't correspond to executable statements. Like you can see here, this is a comment. Here, this is a blank line. Here, this is an opening curly bracket. So those you couldn't execute no matter what, but the ones you want to concentrate on are these ones that never got executed. It's kind of weird that we just ran this program and it looks like it never called the swap function. And I think the only explanation for that is we probably had a bad test file. I wrote a deliberately bad test. Let's take a look at it. This small input file that we just sorted. If you look at it, well, it says I've got 5 numbers, But if you look, the numbers are already in sorted order. So the program didn't have to do much to get those into sorted order. In fact, it only made one pass through the list, and it never found any that it had to swap. So it exited after one pass. So I guess if we wanted to get our code coverage numbers up, we should add a list that it has to do a little more work to sort. Like, we can run the program again and cover more of those lines. Normally, you might run it multiple times under test. So let's run it again, and let's give it a different input in an effort to try to hit some of those other lines. So, and we'll just type in the input rather than storing it in a file. So we had 5 numbers that were already sorted. Let's try an input with 5 numbers that are in backward order. So 9, 8, 7, 6, 5. So 5 numbers are showing up in the input, and they're 9, 8, 7, 6, 5. If we hit enter, it'll put them in sorted order. But I bet that gave us better coverage. This .gcda file just got updated based on the new stuff we just executed. Let's try running gcov again. And you can see, well, we're not at 100%, but we're a lot better than we were before. Let's take another quick look at the source file and see what else we could execute. So going up to the top, and it looks like, yeah, the swap function got executed some now. In fact, all these lines in it got executed 10 times. Looks like the code we're missing is this error handling code. But it'd be easy to write test cases for that. We got a little bit of code that looks for a bad number at the start or a bad number somewhere in the list. Let's just make up some test cases to try to execute those lines. So bubble, how about instead of, so it's expecting a number that says how many items are on the list. Let's give it something that's not even a number. So we got an error message here. It called that error handling function, so that probably got executed a little bit. Let's try, there was also an error test down in the list. So let's try to execute that. Let's tell the program, I'm going to give you 1,000 numbers. And the first one is blah, blah, blah. And that should trigger a different error later in the code. And now if we check for coverage, yeah, it looks like we're up to 100%. So we're executing all 36 of those lines. If we go back to our slides real fast, a lot of what we just did is covered in the slides. So I just wanted to show you that. So here I'm showing, we already saw this. Here's how to compile with support for coverage. Then you run your program like you normally would. And every time you run it, this .gcda file is getting updated. The gcov tool lets you see what your coverage is like. And then if you look in that, in this case, it was bubble.c.gcov, I think. It shows you which lines got executed. We already talked about this. This is how to make sense of the value over at the left end of each line. We went in and tried to get coverage all the way up to 100%, and it wasn't too hard to do that. But we can look at coverage at a little bit finer of a granularity if we ask for a branch coverage instead of just statement coverage. Without any special option, gcov reports on which statements got executed and how many times they got executed. But if you really want to know what parts of your program got tested, you might also want to know, well, what happened inside some of those statements, like the conditional parts. If you write a conditional that has, multiple tests inside it, you might want to know that those conditions got exercised, it seems like, for Boolean conditions. You'd want to know that each of them got a chance to evaluate true sometimes and false sometimes. And you'd want to know if it was a compound conditional with an and or an or in it. You'd want to know that each of those parts of that compound condition got executed. And that's, gcov can tell you that. We don't have to change our options for compiling. But if we just give it this -b option, when we run gcov, it'll give us a report of branch coverage, which parts of our conditionals got executed and or got exercised and which ones didn't. And let's give that a try. So we should still have the coverage from the test we've done already. Let's run gcov-b bubble.c. And you can see, well, for executing statements, we're still at 100%. But within our branches, it looks like we didn't exercise. We're almost at 100%, but we didn't exercise every part of every conditional. And if we take a look at, just updated the bubble.c.gcov file, you can see now it's a little uglier now, but now for every one of our tests, like this if, it tells us how often the test in here did the return value of scanf equal to 1, how often that test went one way or the other way. We ran this program 4 times, and on one of the inputs, we introduced an error here. So no surprise, 25% of the time, this didn't take the body, 75% of the time, it skipped over the body of this if statement. 25% of the time, that one error we put in for this first number, 25% of the time that went and did the body of this if statement. And you'll see that for every one of your conditionals. For loop, there's a conditional. Here was a conditional. We really only had one tricky conditional in this program, and that was in this outer loop of our bubble sort. It's got two parts of the conditional. You can exit this loop whenever the done flag is true, or you can exit the loop once you've taken enough passes. And if you look in the report down here, this first part is how often this test went one way or the other. And the second part is how often this second part of the test, the I is less than or equal to len, went one way or the other. And you can see, well, we haven't fully executed that. We got this test to keep us in the loop, but this test never forced us to execute the loop. So if we wanted to do a good job of testing this, we could go come up with some more test cases to try to get this test to go the other way. But we'd never be able to do it because there's a deliberate bug in this program right here. That was one reason I was kind of vague when I was describing this before. I said, well, if you got a list of n items, you have to take about worst case, about n passes through the list to get it in sorted order. And it's about n, but it's n minus 1 passes. You don't have to take, if you got a list of 5 items, you don't have to take more than 4 passes through that list to get it in sorted order. That's not what this part of the condition says. It says you can stop once you've taken n passes through the list. So this condition is letting us try to take one extra pass that we would never need to take. And that's why this never actually makes us bail out of the loop. It's always the done flag. We could fix this, and then we'd be able to execute. We'd be able to see both parts of this condition go either direction. Let's fix that code real fast, and then we'll run a test, and then probably we'll say that's good enough for this example. But if we go into the original source file, bubble.c, and this is kind of what I'm trying to describe here is what this big comment is saying. This part of the condition is actually a little bit wrong. But if we said, as long as I is less than len minus 1, and that would be the correct condition. Once you've taken len minus 1 passes through the list, you're guaranteed it's in sorted order. So you can stop either if you never had to swap items or if you've taken enough passes through the list. All right, now that we fixed that bug, let's rebuild the program with support for code coverage. And then let's rerun our tests and see if we can get every line and every branch. So we'll just rerun the same test we did before, bubble Let's read input from small input. That was kind of a bad test because the input was already sorted. So we did our own test with the input in reverse order. We said something like, here are 5 items and they're 9, 8, 7, 6, 5. And then it sorted those. And then we had a couple of error inputs, bubble. For the number of items, we gave it garbage. And then we said, I'm going to give you 1,000 items. And the first one's garbage. And I think that probably should have executed everything. Let's try gcov-b bubble.c. And you can see now it looks like we've given every bit of code a chance to execute. All the lines and now even all the parts of the conditionals got a chance to do their job. We couldn't have done, in fact, it's the same test we had before. We just weren't getting coverage of every possible direction a condition could go because one of our conditions was bad. Having the code coverage tools point us toward that gave us a chance to catch that error. And this is what we saw when we were looking at that. This was right before we fixed that error. So that's all the stuff that I thought we would spend time on talking about debugging. We kind of did it out of order so we could cover the more important stuff first, but this should get us caught up with the material. Thanks for your attention. I'll see you in class next week.